Balusek will give a talk unfolding the luminal domain of BTB, the native violator.
Thank you, Dan. All right, thank you everybody for being here. So today I'm going to be talking about some of the previous work I've been doing with out-of-membrane protein BTB. All this stuff that we've been working on, or I've been working on, happens to be dealing with molecular dynamic simulation of BTB in its native environment. And molecular dynamic simulation, for those who don't know, takes and combines chemistry, physics, and mathematics, kind of takes it, puts it into a black box that is highly parallelizable so that we can run on, say, supercomputers. And by using stuff like VMD and NAMD, which was developed at UIUC, and awesome force fields, all atom force fields, we can actually produce trajectories of all atom proteins, lipids, etc., in their native environments and kind of see what's actually happening. So the environment that I'm really interested in studying happens to be gram-negative bacteria. So as you can see, gram-negative bacteria differs from gram-positive bacteria in the presence of not just one, but two cellular membranes that are separated by a region called the periplasm. In this cryo-EM image published by Matthias et al., you can actually see the two different membrane bilayers. And so what we can do using VMD is actually go ahead and create a system which actually contains both the outer membrane and inner membrane. So if we actually take a closer look at this system, we can actually see that the outer membrane and inner membrane are actually quite different. We see that the inner membrane is a symmetric phospholipid bilayer, whereas the outer membrane contains much larger molecules, especially in the extracellular leaflet. So if we take a closer look, we first see that there's these things called lipopolysaccharides. As you can see, they have a number of lipid tails connected to a large core oligosaccharide, which it extends up and actually interacts with these outer membrane proteins. But then you might ask, okay, what are these long chain-like polymers? Those are actually things called O-antigens, and these O-antigens can vary in their repeat units from a couple of repeats upwards of 120 repeat subunits, such that these O-antigens can actually extend out from the cell upwards of hundreds of nanometers. Now, unfortunately, due to time constraints, I can't actually talk about this entire system and what we're going to be going into. So my talk will actually be focusing just in this region, the outer membrane, and specifically an outer membrane transporter. However, if you would like to have a further discussion of this, of course, you can come see my poster tomorrow, and we can have a full discussion about all that's going on in our lab, especially in this region of the periplasm, around the cell wall, these lipoproteins, O-antigens, as well as at the inner membrane. However, what I'm interested in studying is a TunB-dependent transporter known as BTB. Now, TunB-dependent transporters rely on this periplasm-spanning protein called TunB, which is yet to be crystallized, so we don't know what it looks like. However, what we do know is that this TunB-dependent transporters are 22-stranded beta-barrel proteins with these characteristic long extracellular loops, which, as I'll show momentarily, interact with these lipopolysaccharide molecules. It also has a structurally similar luminal domain across all TunB-dependent transporters. It has this highly conserved N-terminus called the TUN box, in which this TunB protein actually binds to unfold this luminal domain. And what we're interested in trying to figure out is, how does the native environment actually affect the protein, and how does it actually modify any kind of structure? How does it enhance some kind of signaling? Those kind of questions. So the first thing we looked at was, okay, let's take two different scenarios. Let's take the apostate BTB. So a thing about BTB is that it relies on calcium ions bound in what's called the aspartate cage, which happens to be right here. You can see those two calcium ions, to actually facilitate the transport of B12 across the outer membrane. And previous studies have actually looked at BTB in a symmetric bilayer, but what we want to do is especially trying to determine how this native bilayer affects protein behavior. We simulated one apostate protein, which means no calcium, in a symmetric bilayer, and then we did two different asymmetric bilayers, two of the apostate, two of the calcium-bound state, to further look at how the bilayer affects it, as well as how does calcium play a primary role. And so what we end up seeing, first off, the obvious one, is the LPS somehow orders BTB's loops. As we can see, especially from the previous diagram in here, is that because of how the phospholipid head groups are much lower than these extracellular loops, we see that there is some binding of charged residues on these extracellular loops to these phospholipid head groups. It pulls these extracellular loops down, whereas in the LPS case, you have this huge oligosaccharide actually blocking the extracellular loops from fluctuating out. And so there's a slight ordering effect. So we can actually observe this using something called root mean square fluctuation, in which we actually look across the entire trajectory at the fluctuation of each of these residues. And what we find in these highlighted regions is that between the symmetric and asymmetric case, there's a great reduction in the fluctuation of these loops. Now you say, why is this important? Well, compared to the B12 bound structure of B2B, these 4 loops are pivotal in binding of cobalamin. So if you can somehow stabilize those, you're going to stabilize cobalamin binding residues. But we say, okay, this is still apostate, therefore, how does calcium play a role? So we say, all right, let's simulate it with the calcium bound in the aspartate cage. And what we see is that in these other three extracellular loops, basically nothing happens. So the LPS is doing its stabilizing effect. However, the one thing that we do see in this one region, calcium has a significant reduction of fluctuation in this extracellular loop. And namely, it actually orders this loop into its very closely bound cobalamin bound state. If we take a closer look, what we can see here in magenta is the cobalamin bound side chains that are considered cobalamin binding residues. And in the blue and in the green are the conformations that these residues take in the apo state, in other words without calcium, and in the calcium bound state. So what we can then see, especially in these highlighted regions, is in the apo state, a number of these binding residues are much further away from their conformation than what we should expect to see in the calcium bound state. So, okay, LPS is doing some ordering. Calcium is actually driving these things to an appropriate binding state, but what else is actually going on? Because it can't just be at the extracellular loops. So then we started looking, okay, how does the membrane actually affect what's going on in the luminal domain? Now, in this case, we're dealing with the apo state in both cases, so that we're actually bearing the same protein. And what we see in the symmetric bilayer is that there's a secondary structural difference here, and we have some side chain differences. So if we look at the native bilayer, specifically in this region, we see again the symmetric bilayer across the trajectory forms up this secondary structural helix in the luminal domain, and it conflicts with what we find in the cobalamin-bound luminal domain. Whereas in the native bilayer, the one that's actually in the LPS bilayer, we see that it follows very closely resembles the secondary structure that we find in the cobalamin-bound structure. Another note of interest is that in the symmetric bilayer, we see this arginine 14, which exists right above this ton box, which the ton box, again, is critical for ton B binding so that we can extract the luminal domain, is actually tightly bound to the beta barrel wall with these 3 residues right here. Whereas in the native bilayer case, we see this arginine actually take a kickback conformation. Now this is very interesting because, as you can see in this orange representation, there's arginine 14 in the cobalamin-bound crystal structure, which, as we see, takes this bent back conformation that we find very similar in the LPS-containing bilayer. This is really interesting. So we say, okay, we see a difference in the LPS bilayer compared to the symmetric bilayer. How is this going to affect unfolding of this luminal domain? So we run some steered MD simulations in which we actually pull on the N-terminus on this ton box of B2B and extract the luminal domain, at least partially. This luminal domain is 138 residues, so you can tell it's probably really long if you try to fully extract it. But just as this first start, we extract to about residue 18, and what we can then see here, running side by side, is that we actually see a much higher force in the S&D of the symmetric bilayer as opposed to the asymmetric bilayer. Namely, this is going to take a little while, I'm going to burn up all my time, that's okay. So full extraction, and what we see is that there's a distinct difference in the two systems between 8 and 15 nanoseconds, and it's a difference of about 250 piconewtons. Now, I'm currently running these S&D simulations to verify that this is actually occurring, and so at this time we can say there is this huge difference, but we do want to make sure that this is not just happenstance. Come on. I'm going to have to wait for this thing to finish. It's the conclusion slide, so. All right, so the effect is likely due to an altered electrostatic environment of the LPS bilayer. So what we can then say is that out-of-membrane protein structure dynamics depend significantly on the environment, both in the extracellular loops as well as what we see inside the barrel. And what we see is that it affects this arginine lock that holds the ton box inside, which may explain the unexpected position of this arginine 14 in the cobalamin-bound structure file, which goes to show that evolution does not make out-of-membrane proteins to function in just any old membrane. We have to really be careful in which membranes we simulate in. With that, I would like to say thank you to my lab, especially to my advisor, who's been going crazy. He has been to 6 conferences this summer, I believe, and so he's been gone. And specifically, I would like to thank funding from the Department of Education, the GAN Award, which actually funded a lot of this work for me and allowed me to stay working with my advisor. And thank you as well to the iPoLS community and everything else. Any type
Okay, I hope I'm not challenging you too much on it, but did you run single trajectories for this, or the results for the force pulling are over like a statistical sample?
So this is actually just a single trajectory of S&D because the system size is very large and quite expensive. However, I am trying to rerun those on our local cluster. I originally used supercomputing time to get the original S&D results, and we were going to end up pulling in actually about 200 angstroms, but as we saw, that was really expensive. So I'm trying to rerun these on our local cluster, which is just taking time.
So without trying to put you too much on the spot, but do you have like some physical reasoning where you can say that like that force difference, there is not really a fluctuation, but rather there is some physical mechanism that you can actually support that plane?
So it goes back to this whole idea behind the arginine lock. As I showed previously, is that the arginine lock actually binds quite tightly to 3 different residues. It forms up a large hydrogen bond network. Whereas in the LPS-containing bilayer state, we see it kick back and it does not form this. So that initial peak that we see is just due to the disconnecting, I would say. And so, but once I rerun these things and get a better idea of it, then I'd love to answer that question. It'd be great.
We'll take one final question while we're setting up. Jose, and these are excellent questions, especially for the poster.
I'll tell you about all the nightmares I have when I do this simulation. I'll get out of it. But I think the barrier you're getting for your unfold is too large because the stream molecular dynamics is not getting all the other fluctuations are in there. So I think your mechanism here is too enthalpy high without enough entropy, and there's lots you can do for a simulation that's too large.
Right. I mean, the big concern there is that we need to be pulling much slower. Is the other thing. This even pulling 1 angstrom per nanosecond is way too fast.
It would be nice to figure out what's the time scale of the fluctuations of the membrane of the protein, but that tells you how slow you have to pull.
Right, right. And so we've actually, so to kind of follow up on that, we've actually run a 2 microsecond simulation with this LPS membrane to see like how much the LPS molecules diffuse, which this is a really big problem. These LPS molecules are much, much larger, and their diffusion constant is 3 to 4 orders of magnitude slower diffusing than your regular phospholipids. So even with a microsecond long trajectory, we don't see these LPS molecules moving or fluctuating in and out much. So that's a huge problem. Thank you.
Okay, well, let's thank hers again.